All right, so let's take a look at today's lesson. We're going to be looking at logarithmic differentiation, but first let's remind ourselves or kind of go back and talk about what kind of derivative rules and techniques have we learned so far. So we've learned the power rule. That was one of our first rules that we learned. Pretty comfortable with that by now. We learned the derivative of e to the x and a to the x. Remember that? A to the x is a to the x ln a. Remember all of that. We learned that. We learned the product and quotient rule. We learned how to do that. And then the chain rule. We also learned how to do implicit differentiation. That's a different type of differentiation where you basically take the derivative of a mixture of variables, x's and y's or other such things. Then we applied that with related rates. Okay, so we're working with the derivative. Today we're going to learn two different things. We're going to learn another rule. This is a rule on taking the derivative of a logarithm. And we're going to learn a different technique called logarithmic differentiation. It's a different technique of doing derivatives. Okay, so we have two things to work on today. One is the rule for just finding derivatives of logs. The other is an actual different technique. All right, so let's first talk about the rules. We have the derivative of ln x is 1 over x. Notice that it's just an x. If it were anything other than an x, we would have to chain it. Right? If it was the derivative of ln of 3x, it'd be 1 over 3x times the derivative of 3x. Right? We'd have to chain it. So just keep that in mind. If it's just plain old ln x, it's 1 over x. Then we have derivatives of log to any base except e. You know, ln x is base e. So any other base, we've got to do this technique. And it's pretty much the same. It's 1 over the argument, but we have a little addition here. We have to multiply by the natural log of the base. Now, that should seem kind of familiar to you. If you remember when we were doing the derivative of a to the x, right? Derivative of a to the x was a to the x ln a. And here, the derivative of log x is 1 over x ln whatever the base is. They're related with each other. I don't know if you remember from pre-cal and algebra 2, but logarithms and exponentials are inverses of each other. So it would make sense that their derivatives have the same kind of look to them. You know, we have to deal with natural log. Now the reason this one, ln x, just like when we were looking at exponentials, why is the derivative of e to the x and not e to the x ln e? Well, ln e is 1. Same issue here. Why is the derivative of ln x just 1 over x and not 1 over x ln e? Well, because ln e is 1. So we just kind of do a shortcut and we don't talk about that. They're really the same. It's the same technique for both. Okay? It's the same thing. So whatever the base is, as long as it's not an e, we would multiply. Notice it's in the denominator. Please note this is in the denominator. So it's actually like we're dividing by ln b. And those are our rules. All right, so let's work on the first one. We're just going to practice this for, I have a couple of problems for us to practice on, and then we will learn the other technique. So we want the derivative of ln of x squared plus 1. So we're going to use this rule. So the derivative of ln x squared plus 1, so d dx equals 1 over the argument times the derivative of the argument. And the derivative of the argument is 2x. That's all the derivative rule that I use, and then I just clean it up. So d dx equals 2x over x squared plus 1. And that is my derivative. Okay, is that okay? Pretty straightforward, yes. Well, right. Well, depends. So when you're multiplying by the derivative, you are just multiplying by the derivative, whatever it happens to be. If it's a fraction that ends up being a fraction, then, you know, basically this is just a whole number because it's not a fraction. So if it's not in fraction form, it multiplies to the numerator. It's a whole number. If it's in fraction form, then you would do the whole fraction multiplying thing. Okay? All right, anything else on that first one? All right. Now on the second one, we could just jump in and just run forward and just, you know, I want you to think about what this one would entail if we didn't use log rules. Okay, I'm going to advocate for log rules in just a moment, but let's talk about what it would entail if we didn't use a log rule here. I would have to do 1 over the argument, so that would create a complex fraction. Then I would have to do the derivative of the argument. Well, let's think about what that would be like. What template would we use to do this? We would use the quotient rule, right? And within the quotient rule, we would have the product rule and the chain rule. So it's doable and it'd probably be a lot of fun, but it would actually be to our benefit for us to expand that logarithm so that our derivative work is easier. See why you learned expanding logarithms in pre-cal and algebra 2? It's because of this. So we want to expand it out so that our derivative work is easier. Now, if you just want to just jump on in, just jump in without doing anything, you certainly could do it that way that I was just explaining. You're just going to get a really gigantic mess. But I'm sure, it'll be fine, right? You could do it. But why don't we try it a different way? Why don't we fully expand it out and then do derivatives? So let's remind ourselves what the log rules are. And notice I'm using log rules because it's a log, right? That's why I'm able to do this. I can't just, just decide I want to turn something into a log. There's a technique for that, and that's what we're going to do next. But this actually is a log. I'm certainly welcome to pull it apart and expand it before I do derivatives. So that's what we're going to do. Do we remember how to expand a fraction? That was a subtraction, right? And how to expand multiplication was plus. And what about exponents? This 2 and this 1/2. Remember, it comes to the front. Okay, so we're going to just pull it all apart like that. We're going to do all of those. Now, just for simplicity's sake, I'm going to do it all in one step. Hopefully that is not too disturbing to you. You don't have to do it all in one step. You can take it in pieces. But I'm going to go ahead and expand it all at once. So I would get 2 natural log x plus natural log sine x minus 1/2 natural log 1 plus x. And that's what I'm going to do the derivative of. Okay, now hopefully that's okay, right? We're all right with that expansion? We've done lots of that before. So now our derivative work is much easier. I mean, it's not, I still am going to have some, chaining to do and such, but it's not going to be to the extent that this would have been had I done all that. All right, so let's do our derivative. So d dx equals, my first one, the 2 is a multiplier. So it's just going to be 2 times 1 over x, or just 2 over x, plus the derivative of natural log of sine x is 1 over sine x times the derivative of sine x, which is cosine x, minus, then my next one is natural log, 1/2 natural log of 1 plus x. So my derivative is 1 over 1 plus x, and I'm going to go ahead and bring that 2 down there for the half, times the derivative of 1 plus x. What is the derivative of 1 plus x? It's just 1. Okay, so that's my derivative. I just need to clean it up. Let's go ahead, just worry about cleaning up individual fractions. So let's do that. Let's clean it up. So I have 2 over x plus, so cosine over sine, I'm going to just tell you they're not going to leave it like that. They would turn it into cotangent. Minus 1 over 2 times 1 plus x. Now, I know I have some people out there that love algebra. And you see this and you're like, oh, I want to add it all together and get a common denominator. Refrain, okay? Don't do that. Unless you just want to. I mean, if you want to have fun adding it together, I'm not going to say you can't have that fun. But it's not necessary. It's not necessary to add it all together. The only time that you would need to add all this together is if you were doing a multiple choice problem and they had added it all together. You would need to be able to recognize what this looked like being added together, which you probably could do without even adding it together. I bet you could probably do that in your head. So that's when we need to be concerned about adding these things together. Otherwise, just let it be like it is. Just leave them as separate fractions, okay? All right? Everybody okay with that? Yes. Right here. Yeah. Well, if it's a multiple choice question, you're going to, have to be able to recognize. But, yeah, just right here. Okay, we okay? So we've just looked at how to use these different log rules. Now we're going to go to the next topic, which is called logarithmic differentiation. Okay, so let's talk about this. First of all, let's look at this right here. Okay, we're only going to use this technique when you are instructed to, because you're going to come out with a derivative that looks different than if you had not used the technique. All right, and they would do that on the, on the test. They would say use logarithmic differentiation, or how would you use logarithmic differentiation, something like that. They're going to talk about it. Now, when do we use logarithmic differentiation? Well, when you're told, right? And the reason that you might be told, the reason I might tell you to do that is because you might be expected to take the derivative of something like that. All right, now think about taking the derivative of that, just pure, right, just off the bat, just jumping into it. We would use the quotient rule, right? And within the quotient rule, we would use product and chain here and chain here. So pretty complex. All right, pretty complex. Please note that this does not have logarithms in it at all. We don't have a logarithm. If it had a logarithm in it, we would just expand it all out and do it like we did the last problem. I wouldn't have to worry about logarithmic differentiation. Okay? Wouldn't have to worry about it. But this isn't a logarithm. And this might be one that I would ask you to use logarithmic differentiation on. And so let's learn how to do that. So I wrote out the steps, 3 steps to do. Step 1, I would take the natural logs of both sides of an equation. Remember, it's an equation. We can do whatever we want as long as we do the same thing to both sides. And then I would use laws of logarithms to simplify. So that's step 1. So we're really wanting to turn it into something that we just did. So it's in little small pieces, so we're less likely to make a mistake. Less likely to make a mistake when it's in little bits. Step 2, we're going to differentiate implicitly with respect to x. Then we're going to solve for dy dx. Okay, that's our structure. So let's start. So just for for simplicity purposes, I'm just going to take the natural log of both sides. Just showing it like this. I'm taking the natural log of both sides. Okay, that's step 1, or for the first part. And then we're going to expand. We're not doing any derivatives yet. We are basically just expanding out. So that I would have ln y equals, and now I'm going to expand that other piece out just all at once, just like I did the other one, right? I hope we're okay with that. I'd have multiplication would be adding and division would be subtracting, right? Okay, so let's expand it all out. So we would have 3/4 natural log x plus 1/2 natural log x squared plus 1 minus 5 natural log 3x plus 2. We're rewriting. We're just rewriting. We're not doing derivatives yet. Okay? We're just rewriting because we really are trying to avoid doing the derivative of this one straight out. Right? So, logarithmic differentiation. We've just completed step 1. We've taken the natural log of both sides. So we did natural log of something that didn't have a natural log in it. So we're understanding the significance here. You only do this when you're directed to, because it's going to come out looking much different than if you didn't. Okay, so, and then we just used our log expansion rules to expand that all out. Now we're ready to do step 2. So we have step 1 down. Step 2 is differentiate implicitly with respect to x. Well, really, the only implicit differentiation I'm going to have to do is on the left side, right? Everything else has got an x. So the derivative of ln y is 1 over y. The derivative of y is 1 dy dx. You can think of it as chaining or however you want to think of it. Okay? Equals. So, and the other part is just regular derivatives. So the derivative of ln x is 1 over x. So that would be 3 over 4x plus the derivative of 1/2 ln x squared plus 1 would be 1 over the argument, and then I'm going to bring that 2 down for the half, times the derivative of the argument, 2x, minus, okay, 5 is my multiplier, I'm just going to leave it there, 1 over the argument, 3x plus 2, times the derivative of the argument, which is times 3. Okay, so on the right side we have some cleanup to do. Notice we've done step 2, and now we've got to solve for dy dx. Okay, we can't leave the y there. We can't even leave the y in the equation. Okay, can't do it. So I need to multiply through by y to get rid of it, right? To move it over here because I got to solve for dy dx. That's what I'm supposed to do in step 3. Solve for dy dx. So I'm going to multiply everything through, or the two sides through, by y. That leaves me with dy dx equals. Now I could put a y here and then multiply, put the rest in parentheses. But to save a space, to save a step, do we know what y is? Yes, we do. Now, luckily, all we have to do is just write that. We're not going to have to do anything about it except write it. So let's go ahead. We know that y would be here. So let's go ahead and put the y there. So that would be x to the 3/4 times square root of x squared plus 1 over 3x plus 2 to the 5th. And then I'm just going to pretty the right side up. Just pretty it up. So it's 3 over 4x plus, notice here my 2's would cancel out, and I'd be left with x over x squared plus 1. And then that would give me 15, 3x plus 2. And those students of mine that love algebra and really want to add that together and, add this together and multiply them, please don't. Just leave it. I know some of you are really itching to do that. Just don't. Okay, just don't resist. Please resist the temptation and just leave it like this in all its beauty. And there we go. That is logarithmic differentiation. Okay, so it's not that bad. Oh, think about what it would be like to take the derivative with the quotient rule, and then we'll talk about that. Okay?